Hello guys, good morning. Welcome to this lecture. Today we are going to talk about the factors affecting the inflow performance relationship. Okay. As we said, this lecture is for the petroleum engineers, the reservoir and production engineers. In fact, everybody working in the oil and gas field, because it is of a vital importance for you to understand the lecture, as you will make use of it to evaluate the reservoir performances and to calculate the productivity of the reservoir. So let's keep the ball rolling. You already know this. This graph. We have explained to you how to draw it and what is the meaning of each item you see here. Okay, as we said, the x-axis is represents the yaw, which is the flow rate, and on the y-axis we have the pressure. And when the pressure of the pressure in the well is at zero, the bottom hole pressure is at zero, we have the maximum production rate. Because as we stated before, the driving force in the naturally flowing well is the pressure drawdown, which is the difference between the average reservoir pressure and the bottom hole pressure, right? Okay, good. Let's focus on our lecture of today, the factors affecting the inflow performance relationship. Okay, these factors are the permeability, which is K, the pay zone thickness, which is H. Okay, that means the thickness is the pay zone thickness is the average height of the formation which is producing the hydrocarbons. Okay, and the drawdown pressure, which is the driving force, of course, the fluid viscosity, the skin factor due to the permeability change, and the formation volume factors. Okay, so overall we have six items that are affecting the reservoir IPR. Okay, so master them well. We have the permeability, the pay zone thickness, the drawdown pressure, the fluid viscosity, the skin factors, and the formation volume factor beta O. How to calculate the flow rate? By using the IPR equation, we can calculate the flow rate Q quickly and easily, because Q is J multiplied by the driving force. Okay, as we said, J is the productivity index and it is 1 over everything that you know, okay, from the Darcy equation. Okay, so you have Q is equal to J multiply the driving force. Okay, from there you can calculate the flow rate. Calculating the bottom hole pressure. Okay, if J remains constant with drawdown, once a value of J is obtained from one production test or calculated, it can be used to predict the future inflow performance. I will state it again: the future inflow performance. The plot will be linear with the slope of 1 over J, negative 1 over J. The minus sign is because the line is declining. Okay, from the left to the right is declining, so the slope is negative. Also, we can calculate the bottom hole following the bottom hole pressure following the equation, the flow rate equation, since we have Q is equal to J multiply the driving force, which is the reservoir pressure, minus the bottom hole pressure. Then from that equation we can derive the equation to calculate the bottom hole pressure and the inflow performance below bubble point pressure. And as we said, I think you already know it, that when you are producing the reservoir, right, the production and means the reservoir pressure, when it is still above the bubble point pressure, you have a one phase flow. Okay, the bubble point pressure, the pressure of the reservoir, because each fluid has its bubble point the bubble point is characterized by the pressure and the temperature. Okay, this is the pressure at which you have a phase change. Okay, when you are producing in the reservoir, normally the pressure of the reservoir declines, right? Okay, so when you are still above the bubble point pressure, you have a single phase diagram, you have a single phase flow. But when you reach, when you go below the bubble point pressure, then you have gas. Okay, then this gas will cause a double or a multiple phase flow. In that case, you will no more have a straight line. Okay, you will have multiple fluid flowing. Then the curve will tend or will have a tendency to deviate, will look like a parabola, or in fact it will change the shape. Okay, after plotting the in dimensionless IPR curves for all cases considered, Vogel proposed an empirical relationship for saturated dissolved gas drive reservoir. As I said, you will have gas once you go below the bubble point pressure. Okay, and this is the Vogel equation, which is a Q naught over Q max. That means the flow rate, the reservoir flow production flow rate over the maximum flow rate, which is obtained at PWF, is equal to 0. Okay, that is the maximum. Then you have the following equation that you do not need to memorize, because it is given in the exam. Okay, so you do not need to memorize this equation. Just know how to get the cure max, the cure, and PWF. Okay, the average reservoir pressure is usually given in the exam. Let's continue with the Vogel behavior. The IPR curve, Vogel plotted the data using the following dimensionless variable. Okay, PWF over P and cure over cure max. That means it is out of these two. After dividing PW, the reservoir, the pressure at the bottom hole. Okay, the bottom hole pressure over the reservoir pressure, and the production, the reservoir flow rate, and over the maximum flow rate. From that, you can plot it on the graph and get the Vogel behavior. Then this is what I have just explained to you, that once you reach the bubble point, right, you do not the you face, I mean, you have a phase change. This phase change is due to the gas that evolved from the fluid. Okay, the gas that evolved from the fluid is, you have the dissolved gas, sorry, the dissolved gas, which cause a multiple phase flow. In that case, you will no more have a straight line, you will have a shape change. Okay, which tends to look like a parabola. This is it. Okay, so for you to draw it right, on the x-axis you put the cure over cure max, and on the y-axis you have PWF over P. Okay, PWF being the bottom hole pressure, and P is the reservoir pressure. Meanwhile, cure is the production flow rate, and cure max is the maximum production flow rate at PWF is equal to 0. Okay, so how to find the Vogel cure max? Mathematically, relation between the Vogel cure max and the Darcy equation. Okay, which is normally known as the equation, the average, the flow rate equation. Okay, Q max is AOF, that means the Darcy equation, over 1.8, which is J multiply P, the average reservoir pressure, over 1.8. The 1.8 is given. Okay, it is a constant. Okay, what you have to know here is that the Darcy equation is the equation of flow, right? Okay, at constant, at a single phase. Okay, that means the pressure being above the bubble point pressure. Okay, so how to find the Vogel cure max? Okay, how to find the Vogel cure max. This is the given equation from which you can derive and get the Vogel cure max. Cure max is equal to cure at the bubble point plus J at the bubble point divided by 1.8. Okay, do not get confused. Okay, always know that P is greater than the P bubble. The Darcy laws apply. Okay, if the pressure is above the bubble point pressure, then it is the Darcy law. Okay, when the pressure is below the bubble point, then you make use of the Vogel equation, which is Q is equal to Q bubble point plus Q max minus Q at the bubble point. Then you have everything in bracket. So how will you, if you've got to plot it, okay, so how will you go about it? Then the first thing you have to do, as I said, you already know that the I mean that below the that above the bubble point pressure, you have a single phase flow, right? Then first of all, draw the straight line IPR, okay, till the bubble point. Then you substitute the pressure by the bubble point pressure. I'm talking about the reservoir pressure. Okay, you substitute the reservoir pressure by the bubble point pressure of the fluid. Okay, there you can get the cure bubble point and the pressure at the the cure bubble point, and you already have the pressure at the bubble point. Okay, from which you can get the flow, okay, at the bubble point with the Darcy equation. Okay, you have the flow at the bubble point. Then from that, you substitute in this equation, in the Vogel equation, and get the cure at the bubble above the bubble point pressure. Okay, and for you to plot the Vogel, right, the only thing you've got to do now is to substitute the difference value, the values of the pressure which are given in order to get the cure at each point from which you plot your Vogel. You plot the Vogel. Okay, then this is what you will obtain. Okay, this is what you will obtain. Then you have, on as I said, on the x-axis you have the cure over cure max, and on the y-axis you have the pwf over p. Okay, please pay attention here. The bold line in red is the Vogel. Okay, the bold line is in red is the Vogel. Had it been we did not apply the Vogel equation, we would have got what you see in dots line. Okay, in this continuous line, this is the Darcy equation applied here. We obtain a reason why, when you want to plot it, right, always first of all find the cure max using the Darcy equation. Okay, well, how to combine the IPR? This is a combination of the Darcy and the Vogel. Okay, the straight line that you are seeing here, right from P up there, and which comes and intersects the x-axis on the right corner, okay, is the Darcy equation apply. Okay, which means the pressure of the reservoir, we consider that the pressure of the reservoir is still above the bubble point pressure, which is not real, because when you are producing the reservoir, once you reach the bubble point pressure, right, you have a multiple phase flow. Then this thing, you no more have a single phase flow, and the Vogel should apply from that point. Okay, reason why, you can see that at a certain point we have the P bubble and the cure bubble point. Okay, once you have the P bubble and the cure bubble point, then you start deviating, and you have the curve which has a parabolic shape, and you can see it is written there that this is the Vogel behavior. Okay, this is the Vogel behavior. Okay, so keep in mind that once you are above the bubble point pressure, you apply the Darcy equation, and once the pressure of the reservoir falls below the bubble point pressure, you now have the Vogel. You apply the Vogel because you have multiple phase flow. Okay, so let's have a summary of the inflow performance equation. The relationships to determine the oil production rate at various flowing bottom hole pressure are as follow. Okay, the first one is Q naught is J multiplied by the driving force. Okay, and the PWF is always is, I mean, when the PWF is greater than the P bubble point. Okay, and when PWF is uh, greater or equal, okay, when the PWF is less than the reservoir point, okay, we also have J is Q naught multiply P minus PWF. Keep in mind that P is the average reservoir pressure. When the following bottom hole pressure is below the bubble point pressure, you have the Vogel equations. These equations are given, and as I told you, you do not need to memorize them. You will be given they will be given to you in the exams, and if you are already working in the field, you can simply enter it on Excel and build your Excel sheet to calculate it. Okay, well, uh the importance of knowing the IPR. Okay, so why do you need to know the IPR? Because in the stimulation candidate selection, okay, and the production prediction, okay, I hope you understand the meaning of stimulation candidate selection, because when you are producing the well at a certain phase, the well, if the well is no, the reservoir is no more producing well, you have to stimulate, and in stimulation you have various fluid for stimulation, fracking, and so on. In fact, that is another topic. Okay, and the production prediction, when once you know the IPR, you can predict the production. Okay, and as I said, this lecture is of a vital importance. So it also helps you to calculate the flow rate and the bottom hole flowing pressure. It affect the effect of the drawdown on the reservoir. Okay, and also it also has an effect on the drawdown on the water oil ratio. And you have to keep in mind that the gas oil ratio and the water oil ratio are very important once you have to evaluate the reservoir performances and the reservoir productivity. So the IPR, it is very important that you master the IPR. Okay, you know the right values and you know how to play and draw and play with the IPRs. So let's have some. I wanted to solve a sample here with you, but I will keep it for the next lecture so that you guys can easily follow up. Okay. So thank you very much. See you in the next lecture. Please follow our channels and share with your mate. Don't forget to click on subscribe and share and like. Our aim is to share the training for students. Thank you very much.